qui est directeur de thèse donc, de Gaspard Aymerich pour cette soutenance. À ma gauche serait Tim Schrabach de Innsbruck, professeur à Innsbruck. Céline Combé, qui est directrice de recherche à Grenoble. En ligne, nous avons Cathy Frommer et Anja van der Linden, qui sont toutes les deux. Alors, Anja qui est à Stony Brook et Cathy Frommer qui est, j'ai oublié où ce qu'elle dit. Mais donc, qui est examinatrice et rapporteuse respectivement. Donc, nous sommes ici pour écouter donc, la soutenance qui sera suivie d'une séance de questions. Donc, tu as dans les 45-50 minutes pour la soutenance et ensuite nous passerons aux questions. Donc, nous commencerons par la suite au rapporteur. Donc, à toi la parole.
Okay, thank you for this introduction. So, hi everyone, and welcome to my PhD defense. Today I'll be presenting you the work I conducted throughout these 3 years about the subject extracting cosmological information from the late-time universe, working with both galaxy clusters and large-scale structures. This work has been conducted here at the Institut d'Astrophysique Spatiale under the direction of Marion and Laura, and at CA again under the direction of Gabriel Pratt. So, let us first start with a bit of context. Sorry, I'll just remove the zoom thing here. I can't. All right. Let's go with it. Okay, let's get back into it. So the standard model of cosmology. This is the current view that we have of the universe and its evolution throughout time. So starting with the Big Bang model, so an infinitely concentrated universe that then very rapidly expands, starts out fully ionized due to the temperatures, and then reaches a point where it becomes neutral again at the recombination point, and then continuing its expansion throughout its history and forming structure during its evolution. The main 3 components of the standard cosmological model are first dark energy, which makes up for most of the energy density in the universe, about 68%, which is a component that is here to explain the accelerated expansion of the universe, but that we cannot see or probe directly. The second most dominant component is dark matter, which is another component that we cannot see or probe directly, making up about 27% of the total energy density in the universe, and is a component that we need to add additional masses to the structure that we see to explain their, for example, velocity structures. And finally, visible matter that we are familiar with, that surrounds us today, makes up for only 5% of the total energy density in the universe, but it's the only 5% that we have direct access to. And so, this cosmological model needs to be able to explain observations that we make of the universe at all of its different epochs, and fit them with a single set of parameters, which is the main challenge of the standard model. And so, what observations do we have? First, the recombination era that I just mentioned corresponds to the emission of the cosmic microwave background, which was observed and analyzed, and it is, for the moment, the probe that yielded the tightest cosmological constraints. Then, the second epoch we can observe, well, not fully today, is the reionization epoch, which will soon be probed with a future observatory and will need to also correspond to our standard model of cosmology. And today we will focus on the final epoch that we can observe, the late-time universe. And the late-time universe and the structures that it contains are a very valuable cosmological probe containing especially a lot of information on dark energy, since it is, as shown on this graph, the dominant component of the universe at this redshift. I mentioned that over time, large-scale structures form in the universe, and this can be explained and seen through cosmological simulations, which is a plot here. So redshift being the age of the universe, the higher the redshift, the younger the universe is. You can see that in an early universe, we have a very homogeneous density field, but then through the combined influence of gravitational forces and the expansion of the universe, structures itself into something that resembles a 3D web, called the cosmic web, containing filaments. You can see, sorry, it's here, nodes and void regions. And so, how can this be used as a cosmological probe? Here, again, are plots from numerical simulations of the universe. but this time not changing the epoch that we're looking at, but changing the cosmological parameters that we're looking at. So various sets of omega n, which is the overall density of matter in the universe, sigma 8, which is the amplitude of density fluctuations in the universe, and W0, which is the equation of fate of dark energy. And as you can see, the shape and statistical properties of the cosmic web highly depend on the underlying cosmological parameters. And so by observing the cosmic web, we're going to be able to fit our observation of the universe and compare them to theoretical predictions, either from simulations or analytical calculations, and constrain the value of the underlying cosmological parameters. The second way we can use the cosmic web as a probe is to disregard most of the cosmic web and simply focus on its nodes, which are galaxy clusters. And so this is another approach to probing the matter distribution, and as you can see here, the population of galaxy clusters that you expect for different cosmological parameters varies a lot. If the amplitude of density fluctuation, for example, is quite low compared to the value that we believe to be reasonable, there are going to be very few massive galaxy clusters, some lower mass systems, but not very high mass systems that we can, for example, observe in this case here, where the amplitude of density fluctuation is very high. And so, observing the population of galaxy clusters that surrounds us in the universe is also a way to go back to cosmological parameters. And so in the first part of this talk, I'll focus on trying to observe the entire cosmic web at once, explain how we can observe it, how we usually analyze it with two-point correlation analysis, and then why we might want to change our approach to cosmological inference with the cosmic web, looking at deep learning-based methods, and finally focusing on the interpretability problem, which was the object of this article right here. So, how can we observe the cosmic web? There are two main ways to observe the cosmic web. First, directly observing the galaxies in our universe, simply looking at the light emitted by the stars. This is quite an easy observation and a logical observation to make, but as we saw before, visible matter only makes up about 5% of the total energy density in the universe. And therefore, galaxies represent a small percentage of the total mass in the density field. And so they are bias tracers. And not only are they bias tracer, but that particular bias is very hard to comprehend because galaxy formation is a still debated subject and not fully understood with work ongoing with simulations and observation. And so the second way that we can observe the cosmic web is through cosmic shear. So general relativity predicts that because gravity is not a force, but a distortion of space-time, light will actually be deflected by large gravitational potentials in the universe. And so if we look at galaxies that are very far, their images will be distorted by the structures that lie between them and us. And so this is a very good probe of the cosmic web because this probes the total matter distribution, actually the total gravitational potential of the large-scale structures in our universe. However, it's quite a difficult signal to work with, as we expect the amplitude of the distortion to be roughly of the percent level. And so it makes it a difficult signal to observe, especially when you know that you cannot access the initial shape of the galaxy, so you're going to have to work strictly statistically. How do we usually work statistically to get information from the cosmic web? The most standard method is to use two-point correlation analysis, and this short clip is an explanation of how that works on the galaxy density field, which is simply looking at all of the pairs of galaxies that we have in the universe and seeing if there's some if the separation, if the frequency of a specific separation varies. And so in this example, you see that you have two peaks. Galaxies in the universe are, in this particular universe at least, are more likely to be separated by this distance and this distance than the rest of the distances. This can be extended to a continuous field, so for example, the matter density field that we might want to work with when working with cosmic shear. And you can work either in real space, as this video shows, or in Fourier space. The information content is strictly equivalent. It's just then known as the power spectrum instead of the two-point correlation function. And so this does extract statistical information from the field. However, this is limited to Gaussian information, which is what's shown in this plot here. On the left is a simulation of the universe, so the piece of the cosmic web. And on the right is a field that has strictly the same power spectrum as the field on the left. And so if you were to analyze both of these fields with a two-point correlation function only, you would obtain exactly the same cosmological parameters at the end. And so what this shows is that the two-point correlation function is not able to extract the entire information from the surveys. And therefore, we might want to move to other methods of analysis, especially with next generation surveys that will be more and more precise, going to smaller and smaller scales where this non-Gaussian information is going to be more important. And so one of the ways that we can do that is through deep learning. There are other ways you can work with higher order statistics, but one of the emerging ways is to use deep learning to work directly at the map level instead of compressing the information through some summary statistics. And so how this can work is you need simulations of the universe for a varying set of cosmological parameters that you then obtain mock surveys from, and you train a convolutional neural network, for example, or some other architecture to predict the parameters from these input simulated surveys. And then, once this neural network is trained, you can feed it the actual measured maps of the universe and obtain a prediction of cosmological parameters. And so this is a very promising way to extract the non-Gaussian information from the cosmic web and is under a lot of development currently. The way we're going to apply this inference pipeline in this work is the following. We simulated the universe only with dark matter simulations for computational time reasons for 57 different cosmologies in the omega m sigma A plane. So we're varying only those two parameters, the density of matter and its amplitude of fluctuation. We obtained 2D convergence map from these 3D simulations via the Born approximation, and we're working in 4 redshift bins that are made to roughly mimic a stage-free light survey. We then generate 900 square degrees tomographic survey, so with these 4 redshift bins, and apply Gaussian noise on the fly during training and prediction, and as well as some Gaussian smoothing to remove the smaller scales at which our dark matter simulations are no longer accurate. And the inference pipeline looks something like this. We feed our mock survey through 2 different neural networks. First, the main one is a convolutional neural network composed of 4 convolutional layers, 10 residual layers, and outputting sigma 8 omega m and their covariances. And the second neural network is a neural network made to mimic a 2-point correlation function approach that first does a Fourier transform of the mock survey to obtain a power spectrum, and then passes the power spectrum through 2 fully connected layers and outputs cosmological parameters in exactly the same shape. And we train all of our models for 1,000 batches of 32 simulated surveys, and then conduct a likelihood analysis via MCMC. And so here are some of the constraints that we can forecast using this model. So this is strictly simulation and forecast, not applied to real data. In pink, you had the deep learning approach to the full CNN model, and in blue, the power spectrum-like neural network. And you can see that there is a potential for a drastic improvement of constraints using this deep learning method that's able to extract the full information from the field. However, this deep learning approach basically means that you are feeding your data through a neural network with 10 million parameters, roughly, which is a complete black box with no physical meaning and no indication of how that information is obtained. And so this is a bit of a problem when you're trying to do science. You want to understand where you're extracting your information, where potential biases are coming from. And so interpretability methods, which is methods to try to understand how the neural network gets its final constraints, have been tried, but results are a bit unclear for the moment. And so we will tackle this problem using a new approach that's unlike the usual a posteriori approach, which is that you have a fully trained neural network and you're trying to understand how its prediction is influenced by the input by changing the input pixel by pixel and looking at the variance in the final constraints. This time we'll shift completely the approach and train the neural network each time with a degradation layer to remove some information from the survey. So we want to see that, for example, if we remove certain scales from the survey, how then the network is able to constrain the cosmology by training it without those scales and then predicting without those scales again. And so to do that, we want to quantify the network's performance in terms of constraining power with each degradation that we try. And so we use 2 indicators. The first, most natural one, is the standard deviation on S8, which is the one parameter that weak lensing surveys are best at constraining. So basically looking at the width in this direction of the final constraints that we obtain. And then we'll also check with h the information entropy of the MCMC posterior, because, for example, if we obtain a shifted degeneracy line in some cases, then S8 might not be a perfect indicator anymore. And so we calculate both indicators for all of our MCMC chains to measure the performance of the neural network's constraint given each degradation. Now, what degradation did we look at? First, we investigated changes of scales. So either changing the smoothing scale to remove the smaller scales which are believed to contain more non-Gaussian information, or working with star transform to be able to select a specific range of scales within our survey. And so here are how the final results look like. So here on this side you have the SA constraining power and the information entropy on that side. In pink are the results obtained via the convolutional neural network, and in blue via the power spectrum approach only for the smoothing scale. We did not train that neural network for the rest of the degradations. And what we can see is that the small scales do not seem to bring a lot of information, because smoothing at either 8, 4, or 2 megaparsec per h does not really change the final constraining power, whether in terms of S8 or information entropy. This is likely because we're working with a stage 3-like survey, which is still quite noisy at those scales. What we can see also is that the larger scales, so 16 megaparsecs and above, only keeping those scales really degrades the performance of the CNN. There's a big jump in constraining power from 8 to 16 megaparsec per h. And this, however, does not affect the power spectrum approach much. There is a slight degradation in constraining power, but really nothing drastic. And this can be explained by the fact that those are the linear scales at the redshift we're working with, where the information is mostly Gaussian, and so the power spectrum is really well suited to extract the full information from the field. And finally, what we can see by looking at all of the constraints together is that scales roughly 8 to 12 megaparsec per h seem to carry the most information. As in, if you remove those scales, you have a significant worse constraining power, whereas if some of those scales are in the information that the neural network has access to, the constraining power is relatively unchanged from the reference case. And so this is quite interesting, because the structures happen to correspond to the transition between the linear and nonlinear regimes at the redshifts that we consider. The next degradation that we looked at was keeping only certain convergence regions. So because the convergence corresponds to the integrated matter distribution along the line of sights, those corresponds to either cosmic voids when working with low convergence regions, the majority of the cosmic web filaments in the rest when working with the middle convergence regions, and finally working with the peaks when, and galaxy clusters when working with high convergence regions. And so this is an example of how an initial map can be separated into the 3 convergence regions. Here are the results we obtained with the reference keeping all of the information at the top, and then several different degradations. This is only for the convolutional neural network. And so what we can see is that in terms of constraining power, the peaks provide the best constraint alone. The high convergence region here are slightly worse than the reference case, but not by much, whereas then voids, and finally the middle convergence regions, which don't bring much information on their own. However, even though they don't bring much information on their own, adding them to either peaks or voids, as in these 2 cases here, significantly improves the constraining power with respect to peaks alone or voids alone, especially voids alone. And finally, what we can see is that combining the peak with the Fourier transform amplitude, so akin to the power spectrum of the surveys, yields performances very similar to the reference. And so, looking at the maps, we can try to interpret those results. Either looking at the low convergence or high convergence regions, we're working with small disconnected regions with a typical scale of roughly 7 megaparsec per h, whereas the middle convergence regions probe much larger connected regions. And what we can postulate is that those regions bring mostly large-scale and linear information, Gaussian information, whereas this is where a lot of the non-Gaussian small-scale information is contained. And this could explain why adding those large-scale information from the middle convergence regions significantly improves the performance of either peaks or voids alone, and also why peaks combined with the Fourier transform amplitude yield a similar performance reference. This has a source of non-Gaussian information in the form of the peak, and a source of Gaussian information in the form of Fourier terms, amplitude, which corresponds to the power spectrum. And so to conclude this first part, here's what we did. We generated mock surveys and then fed them to a neural network, but going through first a degradation layer, which allowed us to remove some of the information contained in the surveys. And then we looked at the final constraining power and how that was affected by the degradation applied. And the main points that we found was that the scales 8 to 12 megaparsecs seemed to hold the most information, or at least were the most important, in that particular convolutional neural network's decision process, and that they correspond to the linear to non-linear transition. Then, looking at convergence regions, we found that the extreme convergence regions, so peaks or voids, held the most information, and which was coherent with previous work from Mathila et al., which worked with a posteriori method, so a completely different approach, but similar conclusions. And combining those extreme convergence regions with a source of Gaussian information, such as the Fourier transform amplitude or the middle convergence regions, yielded the best results. And the final takeaway message from this part is that the constraining power of this neural network inference pipeline is strongest when it's provided with a mix of Gaussian and non-Gaussian information. Now, moving on to the second part of this talk, focusing on galaxy clusters. So this other approach to probing the cosmic web, focusing on only the peaks. How can we use them to constrain the cosmology? We'll first discuss how we can observe galaxy clusters in our universe, then how we do number counts cosmology, the theoretical underlying principle, and then we'll focus on the mass calibration. So first working with hydrostatic masses, and then performing weak lensing mass calibration with either pointed or wide field weak lensing data, presenting results from these three articles here. So, how can we observe galaxy clusters? First of all, what is a typical galaxy cluster? Galaxy cluster that we observe, it's an object that is roughly 1 megaparsec in size and weighs about 5×10 to the power 14 solar masses. Like the rest of the universe, it's containing mostly dark matter, about 80%, and then 16% of hot gas, so visible matter but not assembled under the form of stars, and then finally about 4% of stars making up the galaxies within the galaxy cluster. And because of this multi-component nature, we can observe it at multiple different wavelengths. First, we can work in the X-ray. Because this hot gas is at temperatures above 1 kiloelectron-volt, it emits through Bremsstrahlung in the X-ray domain. And this is a way to probe the gas density squared, and it's also a high-resolution observation given the short wavelength. The second way we can observe galaxy clusters is at the millimeter wavelength, so working with the CMB emission. The CMB photons traveling, which is the oldest light in the universe that we can observe, travel through galaxy clusters, sometimes when they're along the line of sight, and then through inverse Compton scattering, the so-called thermal Sunyaev-Zardovich effect happens, which is the fact that these CMB photons, which are very low energy, about 2.7 Kelvin, are going to be accelerated by the free electrons that are contained in the hot gas within the cluster. This is a way to probe the gas pressure integrated along the line of sight in the cluster. And finally, maybe the most obvious one, and the first way that we observe galaxy clusters is in the optical. It contains galaxies that we can observe. Galaxy clusters corresponds to overlaid regions in the galaxy distribution. But if we're working strictly with the number of galaxies in clusters, we only access the star, which makes up for about 4% of the total mass. So another way to work with optical data to probe the entire mass distribution of the galaxy clusters is to use gravitational lensing. So similar to what was presented in the first part, the photons coming from background galaxies behind galaxy clusters are deflected by the gravitational potential of the galaxy clusters, which are the heaviest objects in the universe. And by observing those background galaxies, we can have access to the total mass contained in the galaxy cluster. And so, now that we know how to observe galaxy clusters, how can we use them as a cosmological probe? I showed that in the simulation plots that visually the population of galaxy clusters seem to depend on cosmology, but we need a quantitative way to work with. And so what we use is the mass function, which is a theoretical prediction of cluster abundance as a function of both mass and redshift. And here is a plot from one of the earlier studies to work with the Halo mass function in constrained cosmology, particularly in 2009, which had two different samples of galaxy clusters, a low redshift sample, so nearby clusters, below redshift 0.25 in black here, and a sample of higher redshift galaxy clusters between 0.55 and 0.9 in blue here. And what these plot shows is that the theoretical prediction of cluster abundance is able to fit both population of galaxy clusters if you include this component here, omega lambda, which is the way that we denote dark energy in our cosmological model. Whereas if we set that cosmological parameter to 0, not included dark energy in our model, then we are no longer able to fit both the low and high redshift together. And so this is the same principle that is applied in the current cluster analysis, but working with much larger sample and better data. And so what we need to perform this kind of analysis are three main ingredients. First, a systematically detected sample of galaxy clusters, because we're wanting to work with abundances. We need a systematic detection which, with a known selection function that we can model. Then we need to link the halo mass and the observable. What I showed in this plot was working with cluster mass, and the mass function is a theoretical prediction of cluster abundance as a function of both mass and redshift, so we need access to the cluster mass, even though from the observable that we just discussed, that is not straightforward. So we need to calibrate a link between the halo mass and what we can actually observe with galaxy clusters. And finally, we need a cosmology-dependent mass function, so a way to make those lines, those predictions vary with the underlying cosmological model. And what we'll focus on in this talk is the link between the halo mass and the observable, because this is the largest source of uncertainties with today's galaxy cluster surveys. And so the sample of clusters that we're going to work with for this entire study is the Planck PSD2 cosmology sample, which is a sample of 439 clusters detected via their thermal Sony-Zeldovich effect. So looking at CMB observation from the Planck satellite. And through optical follow-up, they all have available spectroscopic redshifts, which is very convenient to run a cosmological analysis. And here is what the mass redshift distribution in that sample looks like. And so this sample was originally already analyzed as part of the Planck data releases. And the last study was conducted in 2015 with the R2 data release. The observable mass relation in that study was conducted in two steps. First, using the X-ray observation from XM Newton satellites to calibrate a link between the SD signal, so in the Planck data set, with the X-ray derived masses from XM Newton, which is shown on this plot on the left here, calibrating a link between YSZ, this SD signal, and MYX, the X-ray determined masses. But the problem with using X-ray determined masses is that you need to work with the hydrostatic equilibrium assumption. That is, assuming that your gravitational potential in your cluster perfectly balances with the pressure of the gas contained in the clusters. And we know that to be a slightly wrong assumption from simulations and observations. And this is why in this relation here, there is an additional 1 minus b factor that appears to compensate for the fact that this evolution is wrong. And this 1 minus b factor is known as the hydrostatic mass bias, which was then calibrated in the second step of this mass calibration with weak lensing data. However, this was a study conducted in 2015, and the weak lensing samples were quite limited at the time compared to what we have today. The analysis was run with 2 samples of around 25 clusters, plus an experimental CMB lensing mass calibration. And what you can see is that in the final constraints derived here, with each of those weak lensing data sets, you obtain quite drastically varying final constraints. And this is strictly due to the varying mass biases that those calibration steps yielded. And so this is unsatisfactory because the originally pretty reasonable constraints that you can obtain with a Planck sample are significantly degenerated along this direction because of the lacking mass calibration. And so what we wanted to do was to redo the mass calibration from the Planck sample with better, more recent data sets. And so first, the X-ray calibration sample. It was calibrated on clusters observed with XM Newton, and an important point to note is that it was calibrated on pre-existing XM Newton observation. That is, they simply looked at available data for Planck clusters and picked the one with good quality XM Newton observations. On the other hand, the calibration sample that we're going to use is a full reobservation of the early semi-Observatory sample in the Planck sky, which is basically the highest signal-to-noise clusters in the Planck sky. And because this is a full reobservation, we are working with an SZ selected sample that is likely more representative, of the full SZ detected sample, cosmological sample. Second point is that we have twice as many clusters with available X-ray observation, and we're working with similar mass and redshift ranges. And so this first step was conducted by extracting the semi-Observatory signal from the Planck mass and comparing it with the X-ray derived masses from the Chandra dataset here, correcting for non-cos bias. That is because we are working with a signal-to-noise limited sample, and so near the signal-to-noise cut, you're expecting to have more clusters that are biased high with respect to the mean than low. And so you need to correct for that effect before fitting your scaling relation. Adding the statistical uncertainty and the scatter from our X-ray relation yields this final relation between the signal in the Planck sky and the mass with still the hydrostatic equilibrium assumption. This had a scatter of about 21% and was found to be robust to several fitting methods. Comparing our results with the original Planck results, here's what we see. The main point is that we have a much lower normalization, which is this number in blue here. The difference is about 5 sigma, which is very large, but this is actually expected since we are working with the Chandra X-ray telescope as opposed to XMM, and it's a known problem that the temperature calibration of those two telescopes do not match. If you observe the same galaxy cluster sample with Chandra, you will systematically measure hotter clusters and thus heavier clusters if you derive the mass using the hydrostatic equilibrium assumption. The difference that we found in normalization is fully coherent with a previous study of this problem from Schellenberger et al. 2015, which is a difference of about 20% in the final normalization. And the second change that we can observe is that we have a slightly shallower slope in the scaling relation, with the slope that we found being slightly closer to 5/3 the expected self-similar slope. And finally, we have comparable uncertainties, and even though we have a larger sample, and that can be explained by the fact that we have slightly higher uncertainties on the X-ray scaling relation that we're working with in the case of Chandra data as opposed to XM Newton data. Now, with this first scaling relation between Planck signal and X-ray derived masses calibrated, we can move on to the second step of the scaling relations, which is calibrating the hydrostatic mass bias. So, as explained earlier, X-ray masses need to be corrected for because we use a wrong assumption, slightly wrong assumption, and the way that we correct this usually is via weak lensing data, which, because it's able to probe the entire mass distribution of the cluster, doesn't suffer from the same biases as X-ray derived masses. And so in this first part, we're going to be using weak lensing data from Aymerich et al., which is data from the Canada-France-Hawaii telescope, and we're working with already fully derived masses in that data set. And so we have about 60 clusters in common between the cosmology sample and the Aymerich et al. Galaxy cluster sample. And here is what the calibration of that second part of the scaling relation looks like. So comparing weak lensing derived masses on the x-axis here with SZ derived through this hydrostatic equilibrium calibrated scaling relation from the Planck sky. And so we're working with 56 matches and also 36 clusters that are available in the weak lensing data set that are within the regions of the sky observed by Planck, but do not appear in the cosmology sample. So we're going to be using them by taking them into account as a upper limit of the Planck signal for those clusters. And here are the results that we obtain. So biases of about 0.9 when working with Chandra data and 0.76 when working with XM Newton data. And if we want to compare it with the previous results, Aymerich et al., which worked with XM Newton data as well, our results are coherent. It's also coherent with the result derived with the CCCP lensing sample by the Planck 2015 study, even though we have a much tighter constraint on the mass bias. Now, what are the effects of changing the scaling relation? In the rest of the cosmology inference, this is where it appears. So we constrain the cosmology very similarly to the Planck 2015 study by fitting the number counts as a function of redshift and signal to noise, so redshift z and signal to noise q. Here is the theoretical prediction of the number counts coming from the mass function. And the scaling relation appears in this distribution right here, the distribution of the observed signal to noise, of the expected mean signal to noise for a given cluster with a mass, redshift, and a position on the sky. And so the mean expected YSZ signal is given by the scaling relation that we just calibrated. And so these scaling relation parameters in this first study are sampled within the priors obtained at the calibration step. And here are the results that we obtained. So with in red and blue, red being the Chandra scaling relation, blue being the extreme Newton scaling relation with the updated weak lensing mass bias, and in yellow the previous constraints obtained by the Planck collaboration, and in green the constraints from the 2018 study of the Planck CMB for reference. So we see that we obtain coherent constraints with both scaling relations, so extreme Newton and Chandra, and that is because the weak lensing second step sets the absolute mass scale, and thus the final cosmological constraints. We have constraints that are centered on the same value as the previous Planck analysis, but with much tighter constraints, and thus a slightly higher tension with the CMB constraints. And this really highlights how changing simply the mass calibration allows us to drastically improve the constraining power of the Planck cluster sample. And so comparing now with a bit more studies, so a range of cluster studies in dark blue here, of cosmic shear study in lighter blue here, and finally CMB in light blue here. We see that we are in agreement with most studies of the later in universe, so clusters and cosmic shear. And we are slightly below in terms of essays compared to CMB studies, so for example the Planck 2018 CMB or the recent ACT constraints by Lewis et al. 25. The tension with Planck is about 1 to 2 sigma, so nothing drastic, but still an interesting fact to investigate. Now looking at the same plot, we have the motivation for a second study. The first three rows are 3 recent cluster studies. So the Planck clusters here that we just discussed, the SPT clusters, next by Bocquet et al. 24, and finally the Erosita cluster sample by Giardini et al. 24. And what we see is that 2 of those studies have a preference for lower SA values, while the Erosita study found a higher SA value with respect to the rest. So for the moment, these studies have different catalogs, they have different selection functions, and they have different mass calibrations. And so it's hard to understand where the tension really comes from. And so what we want to do is to analyze the Planck dataset with the same mass calibration as both of those cluster studies, and that is using wide field lensing data from the dark energy survey. And this will also allow us to prepare the analysis of the Planck cluster sample with stage 4 weak lensing, which is going to be available in the next coming years. And so, what calibration sample are we going to be working with this time? So on the right, still the X-ray calibration sample that hasn't changed, the Chandra X-ray calibration sample, and on the left, the weak lensing sample that we'll use. So we have 93 clusters in the Planck sample that lie within the DES observed region of the sky, and we have 29 clusters in common between both of those calibration samples. Focusing on the DES calibration sample, which is the sample that changed compared to the previous study, the good thing about the Planck sample for wide field weak lensing calibration is the fact that the clusters in the Planck sample are relatively low redshift, which means that we're going to have enough background sources for all of the clusters if we look at the distribution of source galaxies in the DES survey. Additionally, the only selection is the position in the sky. The only requirement is the fact that the Planck cluster lies within the DES footprint, and so we expect it to be a very representative subsample. We then analyze the DES data with this following likelihood, so comparing tangential shear profiles with expectations given a hydrostatic mass and a redshift. And assuming a scalarless mass bias, which is the same assumption as was done in the previous studies, we can rewrite this likelihood as this integral here over weak lensing mass. And so we have this first distribution of tangential shear profile as a function of weak lensing mass and redshift, and then the second distribution of weak lensing mass as a function of underlying true halo mass, which in turn depends on the hydrostatic mass bias and hydrostatic mass of the clusters. One problem, though, that we have for this study is the centering problem. Because Planck is a space telescope observing in the millimeter wavelength, and we have diffraction in physics, which means that the point spread function of the Planck satellite is quite large. It's about 7 arc-minutes, which, if you overlay it on top of a cluster here, looks something like this. This is the Planck signal that we can derive from this galaxy cluster here in the middle, which was this over that region of galaxies here. And so what you can see is that this is very smooth by the Planck PSF. And this yields an expected miscentering of about 1 arc-minute given the signal-to-noise that we're working with. And why is that a problem? We're trying to work with tangential shear profiles, and to extract tangential shear profiles, you need a center. And so here's the effect of miscentering on an expected shear profile. So here is the theoretical shear profile that you expect from a given halo. This was, by the way, obtained by Sommer et al. 24. And here are the observed shear profile that you are going to retrieve with various offsets in your centering. So offsets of 0.1, 0.2, and 0.3 megaparsecs, which in the case of our 1 arc-minute miscentering expected by Planck corresponds to clusters at about redshift 0.1, 0.2, and 0.35 respectively. And so what you see is that you definitely need to take the miscentering into account when working with the Planck dataset, otherwise trying to fit this thin curve here with this black theoretical curve is going to yield completely biased results. And so I already discussed the fact that you can obtain a center straight from the Planck data by simply looking at the highest peak of SZ signal, but you can also work with optical data since you're working with clusters observed by DES. And you can try to associate a brightest cluster galaxy with each galaxy cluster, and that can be done either automatically with the MCMF algorithm or by handpicking a BCG in each cluster. Since we only have 90 clusters in a sample, it's still doable. And the problem with the optical centers is that in some cases they are very easy. In this galaxy cluster here, this overdense region of yellow galaxies, the BCG is straightforward to pick out. But a lot of galaxy clusters in the Planck sample actually look something more like this, with many candidates for the BCG and no real reason to pick one over the other. And so what we expect is that this optical detection will be a bit challenging in some cases and might yield some very large outliers, especially since the fact that we're working with a wide SZ prior. And this can be confirmed by using the fact that we have clusters in common between our X-ray and weak lensing datasets. And so we expect, however, the center of X-ray emission to coincide very well with the center of halo mass. And so this gives us a reference center for all of the clusters that we have X-ray observation for. And we can then compare those centers, X-ray centers, with centers derived by the 3 previous methods. And what we see is, as expected, the fact that the SZ center in blue are very accurate. There's no large outliers. However, the precision is quite low. Whereas the optical centers, both automatic with MCMF or handpicked BCGs, have better precision, but there are extreme outliers, sometimes up to R500, so which is really then going to yield a completely miscentered tangential shear profiles. And so what we can do is fit the centering distribution and take them into account when we're fitting the shear profiles that we derived from the DS data. And so this is going to be included in the first distribution that we discussed in the likelihood, the distribution of tangential shear profile given a weak lensing mass as an redshift. And so the other thing that we are going to do is to exclude the inner bin from most of the analysis because it is expected to be the most sensitive to the miscentering. So even though we model it, to be safe, we exclude it from our baseline analysis. And here are all the analysis scenario that we're going to work with. In this talk, I'll only focus on the top row here, which is the baseline analysis, so working with BCG centers, source redshift measurement obtained via BPZ, excluding the inner bin, and working with a fixed mass bias, not allowing for mass or redshift evolution, even though we also looked at those possible scenarios. And in this study, contrary to the previous one, we are going to simultaneously sample both the number count likelihood here on the left and the mass calibration likelihood here on the right. So we are going to be able to take into account the correct cosmological parameters when deriving distances to compute the data in our weak lensing likelihood. And here are the constraints that we obtained. So the baseline scenario in green compared with the previous study of the Planck sample that I just presented in red, and the two studies, other galaxy cluster studies of interest, SPT and eROSITA in blue and yellow respectively. And finally, also including the Planck CMB as a reference. And so what we can see is that we have a reasonable agreement with the constraints derived with SPT clusters and the Planck CMB, but we are in quite a stark tension with the ERAS results from eROSITA, about 2.9 sigma. And putting our results in a bit of a wider context on the right here, and also verifying that we are robust to our analysis scenario on the left, so we find compatible constraints within 1 sigma for all of the analysis scenario, we can see that we once again find a slightly lower S8 value compared to the CMB value of the Planck sample, aligning with most studies of the late-time universe and in tension with the eROSITA clusters. And so to really confirm that this tension with the eROSITA cluster study does not come from the mass calibration, what we did was compare one-to-one every mass that were for clusters that were both in the Planck sample and the eROSITA sample. And we find a very good agreement of mass derived both from the eROSITA cosmological pipeline on the x-axis and then the Planck cosmological pipeline on the y-axis. So really the mass calibration is not where the disagreement between our studies and the eROSITA study comes from. Finally, because our mass calibration are consistent, what we can do to compare the difference in cosmological constraints is to predict the Planck number counts that we would expect to have measured with the Planck satellite with both the eROSITA cosmology and the SPT cosmology. And so here's how the distribution of Planck clusters looks like in redshift bins and in signal-to-noise bins. And in gray is the prediction of our best fit model from the Planck plus Thèse analysis, which of course fits the cluster sample that we fitted it to very well. And then in orange, using the SPT cosmology, and you can see that with the SPT cosmology we still obtain coherent predictions, whereas working with the eROSITA cosmology, we would have expected to measure about 2.5 times more clusters in the Planck sample that actually measure. And finally, taking a look at not cosmological constraints, but constraints on the hydrostatic mass bias, which we included in our analysis, this is what we get. This compares our hydrostatic mass biases obtained with either exciton Newton scaling ration in red or Chandra scaling ration in blue, with many studies from either observations or simulations. And what we see is that we obtain a mass bias roughly of 0.85 to 0.9 with Chandra for our two studies, and roughly 0.7 to 0.75 with the exciton Newton data sets also for both our study, which agrees with predictions from simulations quite well. So the conclusions of this work is the fact that the centering issue of the Planck clusters can be addressed and corrected for in the analysis, yielding coherent results with previous analysis with pointed weak lensing observations. We also have coherent constraints with the SPT results, and even though we have a coherent mass calibration with the eROSITA study, we found finite constraints in quite a high tension. And so the difference likely comes from the sample and or the modeling. And so what is left to do for the future with the Planck sample? The very next step is to move on to stage 4 weak lensing data, which is becoming available in the coming years with Euclid and also LSST Rubin starting to gather data. And so what we did in this work was a bit of a forecasting exercise, replacing the DS lensing data with a mock stage 4-like survey. So that means a much larger sky coverage, about 266 clusters instead of 93, higher source density, meaning less noisy weak lensing profiles. And also we suppose that with progress on simulations, we would be able to obtain a better grasp of the weak lensing mass to underlying halo mass bias. So 1%, whereas for the moment we were working with about 2%. And we also study how the constraining power is affected by fully fixing the hydrostatic mass bias, so trying to estimate the maximum statistical constraining power of the Planck cluster catalog. And what we can see is that the constraining power will improve a lot with stage 4 weak lensing data. So moving from the green contours here, our actual study, to the forecast in blue for LSST Rubin-like weak lensing. But we will actually be close to reaching the statistics limit of the Planck cluster sample, the fact that we only have 439 clusters in that sample, which is somewhat estimated by fixing the mass calibration, by fixing the mass bias. And coming back to the first part, what is upcoming possible projects for simulation-based inference? One thing that we can work with, the very recent advent of generative AI, could be applied to cosmological simulations. So to perform simulation-based inference, we require very large sets of simulations of large volumes of the universe for many different combinations of cosmological parameters. And so for the moment, this is only possible with dark matter-only simulation suites that can probe large volumes, but are known to be inaccurate at small scales because they do not include all of the effects of baryons. Whereas hydrodynamical simulations, which we also know how to perform, are for the moment limited to small volumes if we want to probe many different parameters, cosmological parameter combinations. But, however, they are accurate down to much smaller scale. And so, using the recent progress made with diffusion models could provide a way to actually add baryonic effects to dark matter-only simulations, so simulating large volumes of the universe for many different cosmological parameters, and then painting sort of baryonic effects on top of them to obtain more accurate simulations, which would be very precious in analyzing stage 4 weak lensing surveys, especially that are going to probe very small scales. And with this, thank you for your attention, and I will take your questions.
Questions now? So yes. If you want to leave the room for this, more than free. Okay, so we start with the referees first for the question parts, and I will suggest to start with Anja van der Linden, who is online. So if you can unmute and yes, the camera.
All right. Good morning. Thank you, Gaspard. This was an excellent presentation. Very well done. I also found your thesis very interesting. Very important work there to do and to capitalize on the investment that has been done with Planck and to be able to utilize that cluster catalog going forward. It is a pretty unique data set, as you said, so with spectroscopic redshifts for all of the clusters and really the first large-scale SC detected cluster catalog. So that's great. I also was very intrigued by the other project that went into cosmic shear and using machine learning. I also think that would be very interesting topics, and so it was very cool to see a study that looks into using deep learning technique to gain more information from cosmic shear than just using things related to the power spectrum. And so great work. I have some questions. They will mainly follow what I asked in the report, although I think there's some things that are now a bit more clearer to me from your presentation. So I do want to ask with the cosmic shear and deep learning part. You focused on essentially how much tighter can the error bars get, right, in terms of the statistical constraining power, but I'm still confused about like what does your study say about potential biases that we get from work like this? Like, do we expect any shifts in omega matter or sigma 8 from using those techniques and including the degradations that you talked about? So I might have missed something there. So if you could just please
Yeah.
go over.
So that's we did not mention the point of the accuracy of the prediction, because regardless of the degradation applied, there were basically no bias. In this final constraints picture here, the black dot is the reference cosmology that the mock survey used for the prediction correspond to, basically, and you see that either in, so the pink case is including all of the information, and the violet contours are including only the larger scales, I believe, and there's no bias that appears regardless of the degradation. So this is why we didn't focus on this, but mostly on the tightness of the error bars, because that was what changed with the different degradation. And the fact that there's no biases comes from two facts. First, we're training with the degradation, so it's not like we're changing the data sets suddenly when making the prediction, but also from the fact that this is only a pilot study with quite a simplified mock survey, which is not likely to induce many biases. There's a lot of instrumental systematics that would need to be implemented if you wanted to really apply this to real data, and those might induce biases in the final constraints. But in the context that we worked with, there were no biases that appeared at any time.
I see. So for all of the different degradations that you tested, the bias was always much smaller than the statistic.
Yeah, it always landed well within 1 sigma, so we really didn't focus on that.
Okay, great. That's great to hear. And then also on this part, where do you see the main challenges of applying this technique to actual data?
So I think the main challenge right now is generating very accurate mock surveys, including all of the instrumental systematics, because you're working at the field level. You're even more sensitive to those than, for example, working with the power spectrum. So you need a very, very good model. You need to be able to generate those very accurate simulations for large volumes of the universe and turn them into mock surveys, and that's where most of the work is at currently. The actual deep learning part of the pipeline is relatively well understood, and because it's applied to so many other fields, there's really a ton of work on that. But it's really the simulation part that is the limiting factor. You want to have as large a simulation set as possible, varying all of the cosmological parameters that you would want. So in this example, we only focused on omega m and sigma 8, but you would want, of course, especially with stage 4, to include a dark energy equation of states to get some constraint on that. You would want to include intrinsic alignment and model it for several different intensities of intrinsic alignment. So this enlarges your parameter space and makes it very challenging to cover it, sample it sufficiently with simulation. So really, I think most of the work is on the simulation side.
Yes, agreed. Thanks. All right, moving on to the cluster part. I was super pleased to see a Planck analysis that's using similar weak lensing mass calibration as was done for Wayne the Giants, for SPT, and for Rosetta. But you stopped short a little bit of doing the same technique where we use the hierarchical modeling not just for the weak lensing, but also for the relationship between the halo mass and the SC signal in this case, right? You had a table in the thesis, and it said, okay, these are the priors, and the priors are very tight on the slope and the scatter and the amplitude of the YM relation. So I have two questions. It's like, one, why not let them go free? And actually, my second question is, have you tried it? Have you just tried to like loosen up those priors and just see whether the chains take you to a consistent scaling relation?
All right, so focusing first on why did we use this. The first reason is kind of for this to be a step-by-step improvement on the original Planck analysis, changing only one part at a time to see if, for example, we would have obtained a large deviation from the previous Planck study. This would have been an indication that our weak lensing analysis was not sufficient. And so really changing only one parameter at a time. So in the first study, just keeping exactly the same procedure but improving on the samples, and in the second study, changing only the weak lensing mass calibration, is to really control systematics and see where our changes come from. So that's the reason we do that. Another reason is that working with X-ray data allows you to obtain the constraints on the hydrostatic mass bias, which, while it's excluded from those two recent analyses, as you said, the SPT and Eurosita analysis, is still something that is studied both in observation with the recent launch of PRISM and in simulations. And so it's interesting to get a value for the hydrostatic mass bias on a large cluster sample to compare with other studies. So the second part of your question, did we try to let them free? Not really. What we did was to, though, free the slope both for redshift and mass and the mass bias, and because this is like a subsequent step, it basically is equivalent to letting it free at the X-ray level. You then need to gather all your information on the slope and the mass from the weak lensing data, and so this is very similar to what's being done in the Eurosita and SPT studies, for example. And so that's why we didn't specifically try letting it free. But I would expect that removing the prior on denormalization and slope in the X-ray calibration would just mean that you then got no constraints on the hydrostatic mass bias, like the actual value, but because you could vary your normalization, which would be fully degenerate with it, but the final constraints would probably not change much, because anyway, especially when you're letting your redshift and mass dependence, all of your mass calibration information is basically coming from the weak lensing step.
I'm very pleased to hear that that's part of the future work. Awesome. We're very interested in that. And I completely agree with you that there's great value in the X-ray data that you have for so many of these clusters. That adds actually significantly over what the latest SPT and Eurosita analyses do, where they do not use low scatter mass proxies. We did use that in weighing the giants, but my point is more that if you let the scaling relation, the observable mass relation free, but well, you tie to the low scatter mass proxy, but the scatter and the slope of the scaling relation have a pretty large impact on the number of clusters that is observed. And so the correction that you do in, I forgot, part 2 of this thesis or so, it addresses it only addresses the it doesn't address the the Malmquist bias, the one that you get from having more clusters at the low mass end of the halo mass function. And of course, the halo mass function is a function of cosmology as well. So you really need to simultaneously constrain the halo mass function that is cosmology and the slope and the scatter, because they have such a large impact on the number of clusters that are observed. And you can do that with a hierarchical model where you still tie the observables, the SE observables to the low scatter mass proxies, and just self-containiously constrain all of that without needing to fix the scaling relation in a reference cosmology first. But from what you said, it sounds like that you're thinking of doing that or something like that as a next step. Anyways, I would highly encourage you to pursue that direction.
Yeah, it would definitely be an interesting next step to the study. That even though so the scatter, one thing that kind of puzzles me is the Eurosita study with respect to the scatter, because they use a very large scatter mass proxy and they obtain final constraints that are quite tight. So it would be interesting to study exactly the effect of the scatter, for example, on the Planck sample, which is quite well understood, and for which we have a low scatter mass proxy. Because it's true that the tightness of the constraint of the Eurosita study kind of made me question the actual importance in the final cosmological parameter analysis of the low scatter mass proxy. So it would definitely be an interesting next step to look at.
Yeah, so the scatter does come from the cosmology, right? It comes from simultaneously fitting the cosmology and the scaling relations. I completely agree with you that it looks rather large. But yeah, well, that's the first generation analysis. I have a final question, which is a little bit tongue-in-cheek. You said that the largest challenge for cluster calibration is the mass for cluster cosmology is the mass calibration, which I would certainly agree with. But then you also said, well, the masses are consistent between your Planck analysis and the Rosita analysis, and so the mass calibration cannot be the reason of why you found this, very intriguing result that the predicted number of clusters is so much higher than what you find. So what's going on there? Is it the mass calibration or is it not the mass calibration?
No, for the Rosita study, it's definitely not the mass calibration. There are definitely aspects of the studies that could induce biases other than the mass calibration, both in the Rosita analysis, but also on the Planck side. There are studies, the other ingredients that I discussed for the selection function. There were studies done on the selection function of the Planck sample, and the fact that changing that could change the final cosmological constraints. For the Rosita side, there were hints of contamination in the sample with, for example, the Artis et al. Study that looked at splitting the sample in different redshift bins and finding the fact that there was a suspiciously high scatter in the highest redshift bin, and that that last redshift bin wanted an even higher S8 value, so hints of possible contamination by AGN in that bin. Also the fact that they're working with X-ray derived sample, which is arguably a bit harder to deal with than SZ sample, especially the Planck SZ sample where you're dealing with really high signal-to-noise clusters. So there's definitely other biases to investigate now than the mass calibration. But yeah, objects of future studies.
All right, thank you. I'm done with questions. Well done.
Thank you. So we'll go with the second referee, Céline Combet.
Thank you. Gaspard, thanks. Again, I'm going to echo what Anya said, but congratulate you. This was a very clear presentation. I really enjoyed that. I want to highlight that also you did not say everything that's in the manuscript, because there's a lot, and so you made a very relevant selection for this presentation, and this was great to see. Obviously, Ph.D. in France last 3 years. There's 4 first author paper. This is quite remarkable, and I think this needs to be noted, especially in observational cosmology. This is not something you see too often within the time frame we have in France for this. I also really like the fact of trying to extract as much of this sample as possible. I mean, this is 10-year-old sample now, and pushing it all the way, hopefully with stage 4 survey, to the statistical limit of what can be done is very nice to see. I do have questions. I have 3 pages of questions, but nothing to worry. So you already answered some from the question Anya asked, was also great. I'm going to come back to the first part regarding SBI and CNN and so on, because I'm definitely not a deep learning person, and I don't know much about it. And I was wondering, okay, you make a very compelling case, and we see how data degradation can help. There's 2 things that I noticed and that puzzled me, and you haven't talked about this here, but in the manuscript, I think you also do a Fourier transform. You try to change the data. You keep the same information content, but you change the way the data is fed into the network, and the network does not like that at all. And I was wondering, is there a way to know in advance what architecture is relevant given the format we feed the data in, or yeah, you see what I mean?
Yeah,
okay.
So that is a bit of a complicated problem. And so there's 2 things. There's first the architecture. So here we focus on the CNN. There are other architectures available to analyze images, basically. And so what you're referring to, for those that are not as familiar with all of the results presented in the manuscript, is the fact that performing a Fourier transform of the surveys, but keeping both the amplitude and the phase, so theoretically keeping exactly the same information, yielded terrible constraining power, basically. So this is likely explained by the fact that this particular convolutional architecture is not adapted to work with that kind of data. This can be both the architecture in itself, so convolutional neural networks were developed not in cosmology at first. They were developed for a wide array of image analysis applications, and so mainly working on like real space data, not Fourier space data. So they could be not adapted at all, but there's also hidden there, there's quite a few what we call hyperparameters in machine learning, which is basically parameters of the neural networks that you need to tune to your data. And to keep things consistent, what we did was to keep the best hyperparameters that were found for like the full survey and with all of its information. And we kept that consistent across all of the degradation. So maybe we could find a way to tune those hyperparameters that would make it a bit more adapted to Fourier space data, but we did not try that because fitting hyperparameters is one of the tricky things with machine learning as well. And yeah, we didn't really focus more on the fact that the network was not adapted to Fourier data. We just took that as a fact. But the interesting thing is that if you look at the peak plus Fourier transform amplitude, there it seems to be able to extract some information from the Fourier transform amplitude. So it's really feeding it both the amplitude and the phase separately makes it not work at all, but somehow it's able to extract some of the information from Fourier space. It's a bit of an unclear point for the moment.
Okay, thank you. You also, so still on that part, so I think you said, oh, it's great because with this type of analysis we can, feed in raw data and then we have cosmology. But here raw data is a convergence map. That's not really raw data. We first need to get the convergence map, right? And that's not necessarily straightforward. So I was wondering, is there a way to get it to work with even raw data, or how do you factor in the way the convergence map, the technique to build the convergence map in? And
yeah, so that's why I said there's more work to be done on the instrumental modeling of this. This is really an idealized case. We're assuming that we're recovering the convergence perfectly apart from pure shape noise. And so this is definitely something that would be interesting to look at, and I know that people are working with different type of data, so you could also imagine including the galaxy density in there. There's plenty of ways that you can feed in your raw survey. I would expect that as long as what you're doing does not remove information from your survey, it would not matter too much exactly what you feed it to. Neural network models are pretty flexible, so they would likely be able to adapt to working with either convergence or shear, for example, which are two redundant sources of information. I would expect it to be able to adapt pretty well to differing data type, but it's really the instrumental effects that need to be taken into account.
Okay, thanks. So now moving on to the cluster part. So there's, and I hope I did not misread this, but for all the analysis you've been performing, you always, for the count, you do a binned analysis, and this is a bin likelihood. And I was wondering if you've considered using an unbinned likelihood and what you would expect to gain from that. Is this relevant with this data set, or?
So I know that the SPT, for example, study is working with the unbinned likelihood. I haven't really explored what you would gain from that. I don't think, hopefully, given like the math behind it, it should not change much in terms of like biasing either way. Maybe it would be able to extract slightly more information, but given the numbers of cluster that we are working with, it's probably not going to be a massive gain. But once again, this is something that we did not change because we wanted to keep things consistent with what was done previously, but could be tried. It's always interesting to, for example, keep exactly the same pipeline, but just change the likelihood to unbinned to see if there's any changes in the final constraints from this. I'm not aware of anyone having done that, apply the binned and unbinned likelihood on the same data set. So
yeah, no, I don't think so. Yeah, this is really a curiosity question, because we've seen some analysis using unbinned, other binned, and
it's also one of the other things that you can look at, many differences between analysis that you could look at.
All right, thanks. Maybe this is, I have time still.
Yes.
Page 2. No. Maybe this is still, maybe it's just a detail. So in the first reanalysis you do using the ARPANET masses, so I think you're getting a slightly different hydrostatic bias from what Herbonet did.
Yep.
And the only difference, I think, was that you had, in terms of match cluster, there was only 4.
Yeah.
And for only, a difference of 4 clusters, the difference was kind of drastic. I would not have expected 4 clusters having such an impact, and I was wondering if this is a sort of worry, and if it just means we need larger sample to avoid this kind of things.
Yeah, this definitely was a bit of a worry. I would have expected and liked to find exactly the same value that's what they derived. I really tried all I could. I tried 3 different fitting methods, and none of them found back what they were exactly the same result as Aymerich et al. So yeah, really don't know what's
But do you think it's from those 4 clusters? It's something else, or it's really those that are kind of pulling the fit?
No, I would not believe that's those.
Okay.
Those would be significantly pulling the fit away. I mean, 4 out of 56
I agree.
would be hard to drive it like 1 sigma away with just that. So yeah, because there's not much information in the Arbonnet paper on that part specifically. So it's like this paper presents the entire weak lensing analysis and everything, and like the mass bias is a small paragraph at the end. It really goes over quite quickly over their methods, and so I wasn't able to reproduce their results. But it's true it was a bit of a worry.
Okay.
One thing though to note is that there's a 1 sigma difference when considering this method, so including the upper limits from the non-detected clusters, it is slightly lower when using only detected clusters, which is what Aymerich et al. Did. So it's only 78 compared to 81, which is a bit more reasonable.
Yeah, okay. Thanks. Yeah, that's right. I did not see that. Sorry, I know I have something else. Right. So I understand your answer to Anya to say it's still interesting to get a value for the hydrostatic bias, and so we're going to use the X-ray masses. But in terms of defining the mass observable relation, the X-ray really truncates the redshift range, and so you're calibrating not on the full range. So is this? I guess my question is that for future survey, if we don't worry so much about knowing the value of the hydrostatic bias, is it still better to include the very low scatter proxy, but not having the full range in terms of redshift, or just keeping that? And
so the thing to consider is this: we are working with the Planck sample, and in that case, yes, we're truncating at 0.35, but if you truncate at 0.45, you've got 90% of the sample, basically. So for the Planck sample, it's really not a big worry. That's why we didn't really worry about that. Yes, it goes to almost 1, but there's like 5 clusters after redshift 0.6. So the range that we're really not covering makes up basically nothing in the sample. If you were to use this kind of data set on, for example, the SPT clusters that go at way higher redshift and are also populated at way higher redshift, it would be a problem. And it's even a problem for them with the weak lensing data. They need to include some Hubble Space Telescope data to be able to cover those very high redshift clusters. So yeah, in that case, this is mainly the reason that we really did not worry that much about the redshift range. But it's true that for other clusters sample, it would be hard to calibrate the stimulation only on like the first third of the sample. But in this case, it's really not.
Okay. I have one last question or not? But you sure?
Yes.
No, very sure, because you hinted at CMB lensing and calibrating with CMB lensing. We have next generation CMB data arriving. Can you comment a bit more? I mean, is this going to be the way then to calibrate clusters?
So, CMB lensing, it's a very promising avenue, that's for sure, for mass calibration. For the moment, with the Planck data, it's really not adapted to it at all, I believe. The trying to do weak lensing with a 7-arc minute PSF is quite hard, but it's definitely true that with the next generation stage 4 CMB survey, it's going to be something interesting, and it's will likely be a good complement to actual optical reclensing, because you're probing, because your photons are coming from so far away, you're probing a different redshift range to a kernel, reclensing kernel peaks at much higher redshifts, and so they will be a good way to calibrate, for example, future SZ sample that are going to include lots of clusters up to redshift 2. Those with optical reclensing are going to be very challenging to perform mass calibration on, but CMB lensing is going to be interesting. But I believe that for quite a while, for example, Euclid and LSST data will probably be better to constrain the mass at redshift 0.4, 0.5. This is where they're reclensing kernel peaks, and so it's probably going to be tighter constraints. And also, it's easier to perform the analysis than CMB lensing.
Thank you. I'm done.
Okay, thank you. Now we'll start with the examiner. So there's Cathy Romer, who is there online. So please, Cathy, if you want to ask your questions.
Hello. Yes, thank you again, Gaspard, for a fantastic seminar. Really enjoyed it, and also enjoyed the thesis. I'm sure my X-ray prejudice with my background there, but I don't necessarily have a Rosita prejudice, so don't worry about that. I looked at the web page for the Chandra_Planck_ clusters for this very, very impressive data set. Absolutely love it. But some of those clusters look absolutely useless for hydrostatic masses. So was there any form of cleaning done on your sample to remove the ones that were clearly not suitable for hydrostatic tests?
So, no, we didn't remove clusters from the sample, except for a system which were like double system in X-ray and a single system in the Planck data, because those are not coherent to perform mass calibration on. But one thing to note that I didn't make very clear in the presentation due to lack of time is that we do work with the hydrostatic equilibrium assumption, but kind of in a hidden way, so to speak. We are working with the YX proxy to derive X-ray masses, which then itself is calibrated with proper hydrostatic mass, that is masses derived by looking at the temperature and density profiles and really solving the hydrostatic equilibrium equation. And so even though there's some clusters with quite weird profiles, it's much easier to extract a YX proxy than it is to extract a proper hydrostatic masses. And so we could extract a YX value for all of the cluster in the sample with reasonable accuracy. So that's why we didn't have to discard any cluster.
Okay. Since you've got this plot up at the moment, I'm going to come back to something that Anya talked about, which is the Malmquist bias. And I was just wondering, I mean, I love the fact that for stage 4, you think you're going to be, you're going to get to the statistical limit, but why are you still using Planck? Why don't you use ACT or SPT? Because there you've got so much, you don't need to worry about the Malmquist bias so much.
Yeah, it's definitely true that especially the latest ACT and SPT cluster sample are objectively larger cluster sample with less selection problems. Nevertheless, it's always interesting to extract. There's still information to extract from the Planck sample. I mean, the constraints we obtain are reasonably competitive with SPT constraints, for example, even though we have less clusters. And it's, I mean, all of this kind of cosmological analysis game is to be able to fit any observation of the universe that we have with a single set of parameters. So the more observations you have, the better. You need to be able to fit any cluster set with the same S8 value, for example. And so it's always nice to add another cluster sample to the conversation, especially, for example, in this the second project. The fact that there's this disagreement with the SPT and eRosita cluster analysis, which are kind of like the two latest flagship analysis of very large cluster sample, and so bringing in a third sample to the comparison helps to kind of understand a bit better the discrepancies between the studies.
Yeah, I don't disagree with that, but I mean, do you think that it would ever be possible for you to do a joint analysis across SPT and Planck?
It would probably be doable to add some low redshift clusters to the SPT sample that lacks clusters below redshift. There's less clusters below redshift 0.2 than the Planck sample. It could be an interesting avenue. Just need access to all of the data for the collaborations, but yeah, it would be doable.
So coming back to you were talking about YX. I mean, if we were looking at using the ERAS sample, which you've now got thousands and thousands of luminosities, can't we calibrate more of the Planck clusters if you relaxed your requirement on 10,000 Chandra counts? Or is it the fact that you just introduced so much scatter that that's not going to help?
So if using eROSITA data for mass calibration via profiles is very hard to do.
You can't do profiles, but you could do the luminosities. The luminosity is very well calibrated.
Yeah, but the luminosity is then sensitive to all sorts of biases with cool cores versus disturbed clusters, and so you're kind of losing the main interest of the X-ray being a low scatter proxy. If you're working with luminosity, then your scatter increases quite a bit, and you basically cannot derive temperatures with eROSITA. There's been a paper comparing eROSITA temperature with Chandra, Nixon, and Newton, and they're all over the place with very large error bars. So for direct mass computations, I don't think eROSITA is very adapted to that. It's very adapted to detecting galaxy clusters, that's for sure, but then it really needs another source of mass calibration. It's hard to make its own source of mass calibration, basically.
Okay. So just now coming to, it's not really an elephant, it's more of a goat-sized animal in the room. Your offset with eROSITA. I just did a overlay of our Thèse Year 3 results with your results, and Thèse Year 3 are basically consistent with eROSITA. So again, sort of slightly inconsistent with SPT, and then more inconsistent with Planck. So it's not just the ERAS-1 cosmology that's coming up with this large value of sigma 8. So I wish I knew, but I just don't know what's going on. Do you?
I definitely don't have a definitive answer to that. So for context, the Thèse Year 3 results that we're talking about, these results here. One thing to note is that those have not as tight constraints as the eROSITA, which have very, very tight error bar, basically the tightest error bars from any analysis here, which makes the tensions quite sharp with eROSITA, whereas the tension with Thèse Year 3 is really not that worrying. It's about a 1.5 sigma tension. One thing to note, though, is that this could be linked to the cluster population that you probe, the mass range, which is which is why I didn't really delve into the comparison between our ICM selected samples here and optical selected samples below, because you're really looking at a different range in the halo mass function, probing way more 10 to the 14 and or a few 10 to the 14 solar mass clusters, whereas Planck is basically dominated by 5 so 10 to the 14 solar masses and above. So you're kind of probing a different population. And interestingly, eROSITA is probably the ICM selected sample that is the closest to this. They are probing down to group regime, even though they're excluding some of the lowest richness clusters from their analysis. But yeah, it could be one of the reasons that the DES clusters obtain more similar results to eROSITA. Maybe something to do with our halo mass function not perfectly representing the actual cluster population. So that's something to dig into as well.
I think that's all from me. I might ask you some more questions. It's just more curiosity, but I can send those by email. But thank you very much for those excellent answers.
Okay, thank you, Cathy. Now we're moving to Tim Schrabak.
Gaspard, thank you for this really excellent and very clear presentation, which I very much enjoyed. Most of my questions on the cluster side have already been asked and answered. I do have 2 left, but let's come to the first part. I have more questions there. Yes. Maybe first some basic questions for me, because I'm not working on deep learning. I mean, this has a certain architecture. Did you choose this for some reason? Is this standard, or was there some optimization?
So this project started quite early, and it back then really CNNs were kind of the dominant architecture for image analysis. Now visual transformers are equally as important, if not more important, especially in more non-cosmological analysis. For example, like because they are well adapted to taking enormous data sets, so things like DALI or stuff like this, where you're basically trying to train on the entire internet. Visual transformers are very well adapted to that. Convolutional, maybe a bit less. They are better at smaller sample size, which for the moment we have in cosmology, which is, I believe, one of the reasons why they're still quite widely used, even though there's definitely studies with transformers. And it's actually something that would be very interesting to look at. If we found exactly the same results with a completely different architecture, because visual transformers work in a very different way to convolutional neural networks, this would really strengthen the conclusions. It would not anymore be conclusions on this architecture of neural network extracts information in that way, but more of kind of more real underlying information theory kind of thing, that certain scales hold more information and regardless of the way you analyze them. So it definitely is something that I would like to try. However, the thing is, this architecture was already coded and adapted to this type of data, so this is why we chose it. But definitely something we're trying to explore with the transformers.
Okay. So once you have the network trained, you give it your data vector, you get one value of cosmological parameters. The uncertainties come from mock data sets, or how do you get the uncertainties on the ES8 you quoted in the end?
Yeah, so this method is now more and more being replaced with normalizing flow, which is another way to get uncertainties from this type of inference pipeline. But what we did here was to use a mixture density network. So basically, once the network is trained, you feed it samples from your mock surveyed sets for various cosmologies. This gives you not something that looks like this with like continuous contours. That gives you like basically dots in your probability space. And what you do is you then model the distribution of those points in your parameter space with a mixture of Gaussian at each combination of sigma 8 omega n. So in this case, we used a mixture of 4 Gaussian, I believe, at each point, which you then optimize the variance of, and variance in need of. And then this this mixture density network can be explored via MCMC, which then yields those contours. But because you don't have infinite simulations, you cannot perform MCMC directly into your CNN. So that's how we circumvented that problem and obtained smooth the posteriors.
Okay. And if I understand correctly, you have 4 tomographic bins, which means you get 4 kappa maps as input. How important is that tomography? Let's say when you want to constrain S8, and also when you think if you want to apply this in the future to, let's say, a broader range of cosmological parameters, are there gains in terms of having more tomographic bins in your view, or is there any trade-off?
Yeah, so redshift information is also something that we looked at. I did not present it for lack of time, but what we did was working with the different redshift bins We performed first a redshift shuffling, so at every step in the training or prediction process, just randomly flipping the redshift bins so that they no longer correspond to the actual proper order. And we also tried to sum all of the redshift bins, so working no longer with a tomographic survey, but a single map. And what we found is that the constraining power didn't suffer much, especially for the redshift bin sum. Slightly worse than reference, but basically indistinguishable. Redshift shuffle, interestingly, was quite a bit worse than the redshift sum, even though it has at least as much information, if not more. But apparently the network was not able to figure out that you needed to sum the bins to obtain proper constraints. However, this comes with a big caveat. In this main study that I presented, we did not include intrinsic alignment to make things a bit simpler and to have more differences between the different results. Because if you don't include intrinsic alignment, then your reference case becomes much tighter constraints than if you do include it. And we tried including intrinsic alignment for all of the study that we did. And basically it changed none of the conclusions for the scales or the convergence, made them slightly less clear, but did not change the order of constraining power. But this changed quite a bit when including intrinsic alignment. Then the redshift information became really important. If you have intrinsic alignment, this redshift bin sum constraining power gets much worse because you're no longer able to constrain your intrinsic alignment. And so this is why tomographic surveys are mainly important. It's really to be able to constrain those nuisance parameters. Because if you assume that your convergence perfectly traces the matter distribution without any side effects, then having the redshift is always good, but you already have a lot of information just in the integrated matter distribution along the line of sight. But it's because of nuisance parameters that you need tomographic surveys. And I guess that having even more bins would improve your constraining power on intrinsic alignment, even though we did not try it.
How about dark energy? Would you have an expectation there if it matters?
Then, yeah, probably if you're trying to constrain the dark energy equation of states, you would likely need redshift information. But the simulation sets that we used focus strictly on omega m and sigma 8, so we did not explore that. But yeah, it seems self-explanatory that you would need redshift information for dark energy constraints.
Yes, it's like the figure from beginning you showed, really the information on dark energy from the redshift information. Anything else on this part? And why would you smooth at all? I mean, because you have different choices for smoothing. Yeah. What's the motivation for that?
So the motivation was we're starting from this deep LSS paper, which was really this forecasting how much better you can get from deep learning with respect to power spectrum. And so in that case, to make it, even though it was not a fully realistic mock survey, to make it a bit more realistic, you needed to remove the information at scales for which the simulations are not accurate. If you gave the deep learning information down to arbitrarily small scales, even though it's wrong and you're not able to actually mimic proper data, it would give an unfair advantage. The deep learning would not be representative. And so that's why we chose to have a reference case with that 4 megaparsec per h smoothing, which is a choice that can be discussed as a way to remove the scales most affected by baryonic effects, basically. But we did try smoothing only to 2 megaparsec per h and found that it really did not help a lot, probably due to noise. And right now I'm running things without noise to really make sure that this is the reason why those scales did not add much to the constraining power.
Okay, thank you. And then maybe for the clusters briefly, I liked your comparison for the BCG, where you have then 4 galaxies in this one case, or even more. What happens here in terms of the histogram? I mean, your comparison to the X-ray centers totally makes sense. What do you do here? Is there one BCG here, or?
So you have to pick one, given our framework of analysis. I must say I have no idea which one we picked by hand or by the algorithm there. We did do it, so me and Sebastian both picked BCGs to kind of see where we disagreed. But in those cases, I believe that if this was a simulation and you had access to the underlying dark matter distribution, probably none of the BCGs would coincide with it. I really don't expect the center of the dark matter halo to coincide here or here, probably somewhere in the middle. And so this looks like a recent merger or something like this, very messy system. And so in that case, this is typically the kind of case that yields these kind of wide separation from the X-ray to the optical centers, I believe. And so those cases, we cannot do anything about it. We can include them in our modeling, but I don't see a way to derive a good optical center from this.
And then maybe a last slightly provocative question. If somebody is not from the field and you tell them you get different hydrostatic mass biases for the clusters observed with Chandra versus those observed with XMM, do the clusters care about the telescopes we observe them with, or how would you explain this?
Yeah, so my way of explaining it is that I don't like the term hydrostatic mass bias. I use it because everybody uses it, but I think you need to call it an X-ray mass bias, because there's so much more that goes into it than just deviation from the hydrostatic equilibrium, and that's also why you need to be a bit careful when you're comparing with simulations, because in simulations you're actually getting a hydrostatic mass bias, but in observation you're never getting a true hydrostatic mass bias. And so that's my answer. It's not a hydrostatic mass bias, it's an X-ray mass bias.
I'm very happy with the answers, and I also wanted to say I'm impressed by the broad range of topics you worked on and the 4 papers you wrote in the 3 years. That's outstanding.
Okay, then I will ask the last questions. My colleagues already asked quite a lot of questions. Again, I would like to congratulate you. So on 4 papers in 3 years. So as for everybody, it's an impressive piece of work for 3 years as a PhD. Also, it covers a wide range of topics. So you have the SBI, all the data handling aspects for S-rays, Plancks, simulation aspects to some extent. So that's quite broad range of topics. So actually, maybe I have a few additional questions on the SBI actually. Well, I have all the questions after all. So you showed because typically we start like this, but that's flat sky Born approximations.
Yeah.
Do you have a feeling how the results would change if you have data modeling, non-Born and curved sky?
Yeah, we definitely make things worse for all of the cases. But I really think once again that in that context, the fact that you're flat sky and Born approximation is not the dominant factor. To make it more realistic, those are not the big things impacting. It's the fact that you're working with a limited, either no or limited intrinsic alignment model. You're working with 0 instrumental systematic apart from pure shape noise. So I think those are way more dominant factor than going to curved sky and non-Born. But definitely right now that's what's being done. The cutting edge of SBI is including all of those effects, and it would likely change the results a bit. But I think here, for what kind of conclusions we want to draw, they would not really change massively with those things.
And staying on that subject, actually, for those maps, so I'm wondering first on what kind of box size that you use for this simulation, and second, what would be the challenges, because if you want to have icons and have everything projected, so you need particularly big boxes for having this kind of signal. So do you have a roadmap for maybe avoiding this kind of super large boxes, very costly?
So what's being done here is, once again, because we're not trying to have a perfectly realistic mock survey is this is an assembly of several maps, smaller maps, which keeps the box size reasonably low. But definitely, if you want to apply it to real data, that's not fully satisfying. You would want to work with very large boxes, and I mean, at some point, objectively, in that case, brute force is the best way. If you can afford to have very large boxes, they are better. Otherwise, assembling different smaller maps is a way to avoid simulating multiple gigaparsec scales. But yeah, if you want to include the very, very large scale information, you need very large boxes. There's no real going around that, I think.
Okay. I'd like a question also on the positioning, on this problem of the optical clusters and the fact that you have like a discrepancy in position that you're trying to reconcile. Remember in the manuscript, so you adopted the Rayleigh distribution.
Yeah.
It came out a bit of nowhere. But I mean, I understand maybe where it's coming from, but maybe you could discuss a bit more this.
There's one case where it definitely does not come out of nowhere, and that's for the SZ. And the SZ, if you're working in angular space, which is what we do for when we actually perform the data analysis, this is in physical distance, but for SZ, if you're working, because your miscentering is purely coming from your PSF, you actually expect a Rayleigh distribution. That's really, you are randomly picking along two axes, and that's a Rayleigh distribution. So for the SZ, it's really obvious that it fits very, very well. The Rayleigh distribution, it's really the adapted form. For the optical centers, it's a bit more challenging. This time, if you had a proper BCG for every single cluster, and the only uncertainty was coming from the fact that you don't expect it to align perfectly with your center, a Rayleigh distribution is once again the proper form, which explains why the first peak is very well fitted by a Rayleigh distribution. For the outliers, it's a bit more of a challenge because there's plenty of reasons there. It's definitely not a pure Rayleigh distribution. It's a reasonable enough approximation to mix two Rayleigh distributions, one for the main peak and one for the outliers. But then there's less of a very clear mathematical case as to why it should be a Rayleigh distribution. But it has to be some sort of distribution. And it's a good enough approximation.
Now turning to cosmology, I tweet just two other questions. Now to turning to cosmology, so you focused a lot on omega matter, sigma 8. There is still like a hint at some point of the neutrino, but it was fixed.
Yes.
You tried to do something on that respect.
So we once again in keeping with previous works on the Planck sample, we fixed the neutrino mass to 0.06 eV, which is a choice. You have to. It's true that you can include neutrino mass in cluster analysis. However, if you're sticking with Tinker et al. For your mass function, it's not like freeing the neutrino mass is perfect either. Like you are then working with a halo mass function that's calibrated on fixed neutrino mass with free neutrino mass, and so there's caveats with both. One can argue that leaving the neutrino mass free is a bit better, but it's not perfect either. So there's definitely some reason to fix the neutrino mass. And in the end, it's something that we plan to do in the very near future, but we don't expect a massive difference for neutrinos, and we don't expect the Planck sample to provide a very meaningful contribution to the neutrino mass discussion. So it's definitely something that can be done, but wasn't the highest priority.
Well, that's good that you mentioned the Planck sample. So if you're, the last question, if you had like a cluster survey to design, what would be your ideal one?
So I'm biased towards SZ, cluster survey, probably. At least for the detection, I think they're easier to work with. It's easier to understand the selection function. X-ray and optical really, especially right now in the state of things, have the nice thing that they're very, very large compared to SD surveys. I think in the next analysis are going to work with 20,000 clusters in their cosmological analysis. So that's nice, but I think that right now it's not the dominant point, and that's what we show here in the forecast. Basically, even with 439 clusters, we still have a lot to gain. So I think what we want is a cluster that we understand very well the selection function of, and I personally believe that's a SZ cluster survey that currently is best understood, and something that we can calibrate the mass of. Don't necessarily think that going from 5,000 clusters in the first year as release to 20,000 will bring a massive improvement in terms of like the Poisson constraining power. It will help to constrain the mass calibration, because then you have more sources to look at tangential shear profiles. But if that means that you're going down to the group scales and working, you're basically going to add a lot of clusters that you're going to have near zero tangential shear profiles, because already for the massive plane cluster profiles with stage 3 weak lensing, you're not working with like if you're looking at shear profiles one by one, some of them are completely consistent with zero. So I think that for just adding more and more clusters is not the way necessarily that will improve the constraints the fastest. It's really the mass calibration, and so the plane sample is actually really not that bad in the fact that having low-ish redshift clusters allows for a good mass calibration, and I think this is why it's so competitive. And so maybe something that's really densely populated and going to slightly higher redshifts if you want to work to higher energy, but something that definitely is the most important point is something that's well understood and something that you can calibrate the mass of very well, rather than sheer size right now.
Thanks. Now we'll give the floor to the director of the Thèse, the 3 months.
Okay. Congratulations, Gaspard. I mean, from the manuscript and the presentation, we clearly saw the large amount of work that you did in the last 3 years. I think especially in the question and discussion session, it was clear that you mastered these topics, that you are aware of the context, of the literature, of what is around your research. And that is, I think, very important and not always the case after 3 years of thesis. Also, I think we should stress that you start from scratch on classical cosmology. When you arrived here, you didn't have any experience during your master's, so you caught up very fast on that. I think you made our work very easy in these last 3 years. I mean, you were always super prepared during the meetings, very independent. I mean, at some point, like, we were wondering if we needed to be more on top of you, but it was okay. You are very calm in your attitude, so I think that I overstressed to overcompensate for this. But so I think that, yeah, we had a very nice and productive experience. I hope you enjoyed it. It was challenging intellectually for you, because for us it was very nice, at least for me. And so congratulations, and thank you very much for these 3 years.
Thank you.
So I have nothing else to say. So thank you and congratulations for, at least for today, for the presentation and answering the questions, and for the manuscripts and for these 3 years. So you spent 3 years with 3 supervisors in almost 3 different places, because you were at AS, sometimes at the CA, but also at Polytechnic, because you did also some teaching, and even teaching with me, I mean more than me, for the M1. So it's also something you did during your short time of 3 years, so it's nice that you did all of this all together during this time. Same as Laura, when you mentioned your autonomy and independence, which is nice, as you say, as a supervisor, not being on you every day, which was nice. I also appreciate the fact that you were learning really fast, as Laura was saying. You started really from scratch on clusters, and especially at the beginning, where we touched a bit the data in X-rays. You didn't mention it, but you spent some time on the Chandra mass estimation, etc. That we don't really use at some point, but you did the work and you learned a lot and really fast, which was really nice. And I have just one final question. I was wondering if you take your notes on your phone in font size 4, just so that I can't see, I can't read it, or if there's any other reason.
No, I just never had a pen and paper.
So congratulations for everything, and thank you.
Okay, so about 3.5 years ago, Laura and Marion contacted me and said, do you want to try an experiment? And I said, okay, what's this experiment? So why don't we take a joint PhD student between us in IAS and you in Saclay? I said, hey, that's a great idea. You know, this is going to help with, you know, the local network and everything like that. It's going to help with collaborations between us. What do you want to do it on? Oh, well, Planck and X-rays. I said, what? Hasn't that already been done? Hasn't that already been done to death? So anyway, we started the PhD, and you came along, and you very much impressed all of us and me with your capacities. PhD requires not only scientific excellence, which I think you've demonstrated throughout the 3 years that you've been working with us, but also you can be the greatest scientist in the world, but you can have no impact whatsoever if you're not able to communicate your ideas. And I think your communication skills are very good, not only on the writing side, where from point of view of a native English speaker, not having to correct every line of a thesis is great. But also, you know, the way you present things and the way you answer questions and everything like that. So, excellent on those levels. And basically, to conclude, I think this experiment has been a great success. And in response to my initial reaction on the subject, the fact that you managed to get 3 papers out of it is very impressive. And the only question I'm asking myself now is whether or not this experiment is reproducible. Thank you.
Thanks.
Okay, thank you.
So Anya and Katie, you can move to the other Zoom, okay?
Oui.
Ok. Donc Gaspard Aymerich, donc dans le cadre de ces évaluations, le jury apprécie la qualité des travaux des doctorants, donc le caractère novateur et l'aptitude de doctorants à situer dans leur contexte scientifique ainsi que les qualités d'exposition. Donc nous avons bien regardé tout ça et nous avons été assez impressionnés par la présentation et tout le travail qui est allé dans ce travail de thèse. Donc on peut déjà en être très fiers. Le manuscrit présente une bonne overview, une bonne vue d'ensemble des relevés de 6 éléments cosmiques, ainsi que de la cosmologie des amas. La séquence était très logique et très facile à suivre, donc c'était déjà une bonne présentation de cosmologie. Nous avons apprécié tout ce qui était l'aspect graphique, la présentation de tous les résultats, la littérature et toutes les références bibliographiques étaient complètes. Donc essentiellement ça regroupe bien tout le travail qui va dans ces 3 à 4 papiers bientôt de cette thèse. Au niveau de la soutenance, nous avons aussi très bien apprécié tout l'aspect pédagogique qui a été mis pour enchaîner bien les sujets, notamment en mettant bien en scène au début l'aspect cosmologie, malgré tout le travail qui allait devoir être présenté après, d'amener ainsi comme ça la cosmologie des amas dans le contexte plus général du travail. Donc on a pu apprécier les sujets que tu as pu choisir, il a dû faire une sélection bien sûr, et qui a amené une profondeur de discussion par la suite au niveau des questions et de la présentation aussi de tous les résultats. Aussi il y a des aspects qu'on a pu apprécier, disons en sous-jacent, c'est tout l'aspect technique qui a dû aller dans tous ces sujets du point de vue développement et des outils qui ont été nécessaires à faire toutes ces analyses, et donc nous avons très bien apprécié ces aspects-là aussi. Les questions, tu as répondu de manière excellente, au point, sans aller dans d'autres détails que ce qui était nécessaire pour répondre aux problèmes, et il semble que tu aies une très bonne connaissance en effet de tout le contexte pour pouvoir bien sûr resituer tout ce travail. Donc en conclusion, nous t'encourageons fortement à continuer en recherche et à continuer de développer ces aspects-là. Et à ce titre, donc j'ai oublié la dernière phrase, le jury s'est réuni pour la séquence doctorat et d'essayer de décerner le titre de docteur de l'Université Paris-Sud de Saclay. Et avant cela, il faut que tu relises un petit texte qui est ici.
Alors, donc, le petit serment du docteur pour ceux qui ne sont pas très familiers avec la cérémonie. En présence de mes pairs, parvenus à l'issue de mon doctorat en astronomie et astrophysique et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Je pense que je n'ai pas la peine de faire en anglais.
Non.
Très bien, donc c'est l'heure du petit discours de remerciement. I'll start in English for the jury members. Thank you very much to all of you on Zoom and those who could make it in person. Thank you for taking the time to read the manuscript and to come here for the defense. I hope it wasn't too boring, that you had a good time. And so yeah, thanks again for taking the time for this. Then, like the thesis advisors, so all three of you, I'll keep it in English for Laura. I really enjoyed this time with you. I think that we found a good work dynamic where you definitely left me some independence, but still really were there anytime I needed. Were very available, easily reached. I didn't spend quite as much time as maybe initially ambitioned at CEA, Gabriel, because of some problems with the initial contract, and the fact that I didn't want to have two offices and constantly be switching, but I think that nevertheless we were able to meet regularly enough and went to conferences together as well. So this was a very nice, yeah, thank you for those 3 years. It was a really good time. Donc ensuite, je pense que je vais pouvoir passer en français. En dehors, en dehors des encadrants, il y a tout le reste de l'équipe et du labo, bon, principalement de l'équipe parce que c'est vraiment le cadre quotidien que je souhaiterais remercier. Je pense qu'on est une équipe où il y a vraiment une très bonne ambiance de travail. En tout cas, moi, j'ai beaucoup apprécié. Il y a du dynamisme scientifique. On arrive à travailler sur des sujets très différents, mais quand même, en dialoguant assez régulièrement, il y a une vraie vie scientifique qui est animée principalement par l'équipe de permanents. Donc, Laura, Adélie, les chefs d'équipe, puis Nabila qui s'occupait avant des Cosmo Meetings. Je pense que c'est vraiment très important ce que vous faites. Et ça participe vraiment à la bonne vie de l'équipe et le fait d'avoir envie de venir au labo malgré les 45 minutes de RER. Voilà, ça motive de savoir qu'on va arriver dans cette bonne ambiance et de se retrouver donc à la fois pour la vie scientifique mais aussi pour plein d'autres choses. On déjeune tous ensemble le midi et enfin, il y a toujours une bonne ambiance et toujours pas mal de gens présents au labo et ça rend vraiment le travail beaucoup plus agréable. Les gens au labo, donc il y a dans l'équipe, mais il y a aussi tous ceux des autres équipes, spécialement les doctorants, que je souhaiterais remercier, parce que pareil, il y a une vie commune franchement assez active. Donc je ne participais pas à tout en habitant à Paris, c'était un peu plus dur les soirs tout le temps de rester ici un peu plus tard, mais c'est vrai qu'il y a quand même plein d'activités qui sont organisées, et ça participe à la richesse de la vie du labo. Et plus spécifiquement dans l'équipe aussi, les doctorants, je pense qu'on forme un groupe vraiment très, très soudé et qu'on a passé plein de beaux moments ensemble, donc à l'échelle de l'équipe et aussi à l'échelle du bureau. Merci à Gabriel par exemple d'être venu pour ma soutenance, ça fait plaisir de te voir. Et puis merci à Anaïs et Morgane, qui étaient les compagnons de bureau de ces dernières années. Je pense qu'il y avait une super ambiance dans le bureau et que ça participait vraiment au fait que c'était une expérience très plaisante cette thèse. Et ouais, ça va beaucoup me manquer de cette ambiance. Et ensuite, en dehors du labo, merci aussi à tous ceux qui sont venus ici, donc ma famille. Voilà, je suis le dernier à devenir docteur dans la famille. J'espère que les gens n'en ont pas marre des soutenances. Merci beaucoup d'avoir fait le déplacement, d'être venu ici. Ça compte beaucoup pour moi. Merci aussi à tous mes amis qui sont venus, donc de Polytechnique principalement. Et les membres du groupe aussi, c'était toutes les semaines se retrouver, c'était toujours un super moment dans la semaine qui redonnait plein d'énergie à chaque fois, c'était très cool. Et enfin, merci à Inès d'avoir été là dans les 3 ans. Et voilà, je vais m'arrêter là. Oui, j'ai dit on va passer au pot. Juste là devant. C'était peut-être pas très clair.
We are closing the connection. Okay. Thank you very much for attending it. Hope to see you.
And Anya will make the call.